Welcome back to Cinderella Math. This is a part two of the study guide for the second exam in a Calc 2 class. This is being recorded in early March 2026. My pen started to die, so I needed to pause on part one. It should hopefully be back now. So if you're looking for part one, just look in my Calc playlist. It should be there. I can try to remember to link it in the description box, but this is part two. This one should be the quicker of the parts. So let me go ahead and grab the paper here. And we're on, I believe, number 7. So we only have 7, 8, 9, 10. Yes. This whole thing is integration techniques. And coming here to number 7, we are doing some partial fraction decomposition. I'll go ahead and cover up those answers. This is probably the easiest question on this study guide here. It's because we don't need to solve. We are just filling out the partial fraction decomp here. So you want to factor your denominators if possible. So looking at A, that's a trinomial. I factor with the magic X. You factor however you want. There's a 1, there's a 1. First times the last would be negative 72, and your middle number is 1. Multiply here, add here. What if you had 9, spend 8? That would multiply to negative 72 and add up to 1. So the top would be fine, and the bottom would factor as x plus 9, x minus 8. And we could split this into two fractions, one with a denominator of x plus 9, one with a denominator of x minus 8. And since this is linear, by linear I mean this power is 1. All we do is put an a. And same here, this is linear, this power is 1, put a b. When it's not linear, I'll show you what we do then, but these are fine. And that's the answer to A. All right, pause me there if you need to. I'm going to clear to do part B. Okay, part B, let's factor the bottom. Now that's not a trinomial, but looking at this bottom, I see a greatest common factor of x squared, which will leave 1 plus x squared. Okay. And then we're going to split that into 3, y3. When you have a factor that is x squared, first you do an x, then you do a squared. That's just the rule. I'm sure there's a reason. I don't know it off the top of my head. And then we'll do this one. Okay, since this is linear, it's a 1, give it an A. And then the rule here is on the square by itself, give it a B. And then this one, since it's a 2-piece with a square, so it's a quadratic, give it a CX plus D. So if this one's a quadratic, you give this one a linear. If this one's a linear, you give this one a constant. And again, I'm not quite sure why this one just gets a constant. It's just the rule. I'm sure there's a reason. I can't think of it right now. Okay, so that is your answer right here. There we go. Don't put that. There we go. And it said do not solve. So that's all we need to do there for number 7. Okay. Now we're actually going to use this method to solve. Coming to number 8, we're going to evaluate this integral with partial fraction decomposition. So we are going to go ahead and factor the bottom. I factor with magic X. You do whatever you want. 4 times 1 is 4. Middle number is 5. Multiply here, add here would be 4 times 1. So this would be 12 over x plus 4, x plus 1. Actually, let me switch that. It doesn't really matter. It's just how I did it previously on another thing. There we go. Okay, but when this first number, this A coefficient is not a 1, when we multiply, that's really cheating. So we need to divide that coefficient. So that'll give us 12 over, this will scooch up to be 4x plus 1, and 4 divided 4 will just be x plus 1. Okay, if you factor differently, that's fine. You should still come up with this as your factoring answer. And now let's decompose that. So 12, blah, 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 equals A, 4x plus 1, B, x plus 1. And again, it's just A and B because those factors are linear. The power of x is just 1. Okay, but I would love to add those fractions, so I need a common denominator. So I need to bring 4x plus 1 to the B side, and I need to bring x plus 1 to the A side. So just looking at the top, we'd have A, x plus 1, plus B, 4x plus 1 equals 12. And then the bottoms, they would all match now. So let's just ignore the bottom. And now we would like to find A and B. So let's let x be negative 1. And here's why. Negative 1 plus 1 is gone. So that's A times 0, which is gone. Okay, so now keep going. Still letting x be negative 1. So this would be B. 4 times negative 1 is negative 4 plus 1. So that would be negative 3b, and that still equals 12. Divide, and b is negative 4. Okay, now we want a. So we're going to let x be negative quarter. Basically set this to 0, right? So a is negative quarter plus 1 plus b, 4 times negative quarter plus 1 equals 12. Solving the red, this would be 3/4. This would be 4 times negative quarter is negative 1 plus 1. This is 0. B times 0 is gone. So this is 3/4 A equals 12. Times by 4/3 to get off your fraction. So that's 48/3, which is 16. So A is 16. I mean, that's just a lot of algebra. None of that's difficult algebra. You just got to be careful with all your integers, be careful with your fractions, all that good stuff. So we just got that A is 16, and that was over 4x plus 1. So you're back to this here. And then we're going to integrate that with respect to x. Plus, we just got that B is negative 4 over x plus 1. So we're back to here. And we're going to integrate that with respect to x. Okay, I'm going to go up over some stuff, so pause me if you're still writing or absorbing. Oh, and this whole time we've been going from 0 to 1. I'll bring that back at the end. Okay, I am going to bring this constant out. So we're going to have 16, 1 over 4x plus 1 dx. I would love the derivative of the bottom. Well, that's just 4. Let's put it. And then we'll have to put a 1/4 to uncheat. 16 times a quarter is 4. And then this is now 4 dx over 4x plus 1. If you let u be the bottom, and then du, whoops, not x. This is now 4 du over u. And you should just kind of recognize that as natural log of the bottom. So that's going to be 4 natural log of 4x plus 1. And I am putting an absolute value because natural log can only be positive. Okay, that should just, you should recognize that if you're this far into your calculus journey, this going to this should just come. Okay, let's mess with the second one. So I'm going to remove the negative 4. So it's really plus negative 4, but that's just minus 4. It looks better. And then we have 1 over x plus 1 dx. Again, if you let u be x plus 1, du is 1 dx. So this is now negative 4 du over u. That is the same. So this is going to be negative 4 natural log of that bottom, which is x plus 1. And we are going from 0 to 1. Okay. I'm going to go up over the top again. Sorry. All right. Everywhere you see x, give it a 1. So we're going to have 4 natural log. 4 times 1 is 4 plus 1, so 5 minus 4. natural log 1 plus 1 is 2. So there's our first input. Minus, put in 0. So this will be 4. Natural log, put 0. So 4 times 0 is 0. 0 plus 1 is 1. Minus 4. Natural log 0 plus 1 is 1. Okay, so that's now 4 natural log 5 minus 4 natural log 2 minus natural log 1 is 0. 4 times 0, this one's gone. Natural log 1 is 0. 4 times 0, this one's gone. That's just 0. So this is answer. 4 natural log 5 minus 4 natural log 2. Now, my students' program took this. It's fine. If you want to, yes, you could pull out the 4 and have natural log 5 minus natural log 2. But remember your natural log rules. When you're minus, you could really divide. So you could have 4 natural log 5 halves. And then if you really wanted to, this could go up as an exponent. So natural log of 5 halves to the fourth. Oops. And then you could fourth that out. You could take it 4 times, so that would be what? 625 over 16. That's probably the best answer. But again, my students' program took way up here. So why like waste the time if you don't need to? There you go. If you want to check that, we could come to Desmos and type the original integral. And then we got 4 ln 5 minus 4 ln 2. There it is. If you wanted to be fancy and you did ln of 5 halves times 4, there it is. If you took that power up and you got ln of 625 over 16, there it is. So it's all the same. Potato, potato, whatever you want to do there. Okay. Determine whether the integral is convergent or divergent. So this one's just ready to be integrated. So we have integral from 1 to infinity. Now, yeah, we're not technically supposed to do the infinity, but I do it anyway. It's fine. 5x to the negative 6 dx. Integrate. So that would be 5, add 1. So that's x to the negative 5 over negative 5. This could simplify to just negative 1, x to the negative 5, which could be negative 1 over x to the 5th from 1 to infinity. Okay, yeah, you're not really supposed to use infinity. So technically, we're going to make this like an n, and we're going to say limit as n goes to infinity. Okay, that's what you're technically supposed to do. I'm going to come over in orange. So this is now negative 1 over, no, limit as n approaches infinity, negative 1 over n to the 5th minus negative 1 over 1 to the 5th. So I plugged in n, plugged in 1. So this would be negative 1 limit as n goes to infinity of negative 1 n to the 5th minus minus would turn plus 1 over 1, which is 1. And what would be the limit as n goes to infinity? Well, this would be negative 1 over huge. Negative 1 out of a million bajillion is nothing. Nothing plus 1 is 1. This converges and it converges to 1. Okay? There's not really a way to do this on Desmos because you can't input infinity, to my knowledge anyway. But we could input something really, really big. So let's see. That problem was integrate from 0 and then, or no, it was 1, wasn't it? It was 1 and then something super big, like a billion, okay? And then it was 5x to the negative 6 dx. See, they don't like it. There we go. So you don't have to mess around with how big you go, but again, that doesn't show any work, but it's nice to check, okay? And we have one more problem here. Number 10, same problem. Is the interval convergent or divergent? So let's rewrite this as integrate from negative infinity, and yeah, again, I know we're not supposed to, it's okay, to negative 1, 1 over x. This has got an invisible 1. Remember how to turn radicals to exponents? So that'd be 1/7 dx. Bring that up. So this is the integral x to the negative 7th dx. I cut the 1, right? Integrate. Add 1, which is 7/7. So this would be x to the 6/7 over 6/7. This would flip up. So we have 7/6 x to the 6/7 from negative infinity to -1. But again, technically we're not supposed to do it that way. Let's say we have the limit as n approaches negative infinity, 7/6 x to the 6/7 from n to -1. Okay, plug in. So we would have limit as n approaches negative infinity, 7/6 -1 to the 6/7 minus 7/6 n to the 6/7. -1 to the 6/7, that's really 7th root of -1 to the 6th. So that'd be 7th root of 1, which would be 1. So this would just be 7/6 times 1, so that's 7/6 minus 7/6 to the n to the 6/7, and then it's still the limit. So plug in negative infinity. That would be like 7/6 and then the 7th root of negative infinity to the 6th. Well, that would then be infinity because a negative to an even. And then that would still be huge. This is just huge. So you have 7/6 minus 7/6, huge. This is not a number, right? Even if you pulled out the 7/6, you get 1 minus huge. This is 7/6 times negative huge. This is not a number. It diverges. So you need to type in this box, diverges. Watch your spelling. And there you go. It doesn't have an answer. Can't do it. We tried. No, no go. And again, you can't really put this one through Desmos. Negative, do a really big number. And then what was it? 1 over x to the 1/7. I don't think they'll do the 7th root. Just do it like that. Dx. See, that gave an answer. Let's make it smaller, smaller, smaller. See, there you go. See how it's just getting small and small and small and small? It's going to negative huge. It's diverging to negative infinity. See? Again, not the best method to check there, but you can see it's not going to a number. Okay? Diverges. All right, sorry for the 2 parts. Hope this finds you well, and I hope this was helpful. Have a great night. Bye-bye.